we're going to start today with this problem, which was in our notes. And it's this graph that looks like this on page 375. And on page 374, the page before, they give you these little tables to fill in with the values of the function. And that's kind of what we were looking at last time. So here is in Desmos is a picture of the graph. And it has these two sort of parts. It has the quadratic-y part on the bottom and the part on the top, and they look different. Let's make this better. Okay. Can I shrink this? So this is what the function looks like. Can I zoom out? Okay. And there's x equals 1. That's what we care about in this problem. We're talking about sequences that get really close to x equals 1. What do the y values do? So when the x values get close to 1, what do the y values do? And in Math1030, you had a few different options. What could the y values do? Maybe they go to 1. Maybe they go to -1. Maybe they don't exist. Maybe the limit could be 0. Those are the options. And we're going to reveal what they are in a second. But any questions or comments before we get started? Yeah. Sorry? Could it be 2? Like the value 2, or could there be more than 1? So this is the thing. That's essentially what we want to get to here. For sure, for a given sequence, if we nail down one sequence, we say like, this sequence is the one we're looking at. There can only be one limit. But in this question, I'm saying, we're thinking what happens in general for any sequence. So if there's more than one sequence of x values, there could be more than one value for the limit of the y values. So for any one sequence, there's absolutely only one limit, but there's more than one x value sequence here. We're thinking of all the possible x value sequences. And so the question is, yeah, what could happen? So that's exactly what I want to get at, is this question. And I'm going to start by showing you one sequence. And that is this sequence. Here it is. Here's some x values. And those x values are getting really, really close to x equals 1. So they start at 0.5, and they work their way up to 0.6, 0.7, 0.8. And they get really close to x equals 1. So here we can see what's happening a little more zoomed in. So the x values in this case are getting really close to x equals 1. And the question is, what are the y values doing? And you can see them doing something. So they start at like negative 0.3, 0.5, 0.6, and they keep going down, 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 and they get really close to something. In the notes, this is a little table. So let me keep playing this. We'll do this little two-screen thing. You guys don't want that? Okay. I will do this thing in the notes. Okay, let's try that. Okay, and I want, oh boy, lots of funny stuff going on here. Okay. I want, in the notes, the 430 version. Okay. Oh no. Please go away. Okay, thank you. So I want to fill in this little table of values. So here's the function. And what is the function doing? We're looking at these values, these x values. These x values are all a bit less than 1. A bit less than 1. Okay, and we can see what it's doing over here. The y values, they go down, 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 and they're supposed to be getting closer and closer to -1. Okay, everything is all wonky on the, here, maybe I zoom out a bit. Okay, so we can fill in some values. When x equals 0.5, the y values are what? It's negative 0.25. Okay, and you can see that on the graph if I stop this guy and I slide it to where I want it. When x equals 0.5, y equals negative 0.25. And the next thing on the graph is 0.9. So when I slide this forward a little bit more, now when x is 0.9, y is negative 0.81. So I can put that in, negative 0.81. Actually, let me do these in red so we match our thing. Negative 0.25, negative 0.89. Okay. Then, if I keep going even more, when x is 0.99, y is negative 0.98. 0.98. Okay? And what you should notice is that the y values are getting closer and closer to something. If you kept doing this, you would get negative 0.998, negative 0.9998. They're getting closer and closer to negative 1. So these get close to y equals negative 1. So the x values as the x values get closer to +1, the y values get closer to -1. And we encapsulate this fact in this sentence, and we say, as x approaches 1 from the left, f of x approaches y equals -1. And this is a very special sequence. It's all coming from the left. The x values are always a bit less than 1. The x values are a bit less than 1. And you can see visually it's called on the left because on the number line, being a bit less than 1 means you are on the left. So if you keep playing it, I'm never looking at values of x that are bigger than 1, always a little bit less than 1, always to the left of that dotted line, x equals 1. Okay, so what in this situation, the limit of the y values is -1. So the correct answer in Math1030, because of this sequence, is definitely going to include, it's going to include this first option, that the limit could be -1. Let's see how many people said different things. So that one is definitely correct. The limit could be -1. Most people got that one. 18 out of 28 people got that one. Could the limit do other things? Could the limit do other things? So you have the full picture now. I think you understand the question. That was one special sequence of x's. What happens in general? Could other things happen? And I'm going to give you another minute to revote and think, now that you've seen this example, could other things happen to the limit, or is the limit always -1? And yeah, I'll give you one more minute to try this one out. So I'm going to repeat this one. I'm going to exit this. I'm going to repeat it, and you can vote again on this one. We're going to start this one, and then I'm going to present it. Okay, so I'll give you 2 minutes to think about that. We've seen the limit could be -1. Now the question is, could the limit be other things? Yes or no? I'll give you 1 minute to work on that. Okay, 10 seconds left. 10 seconds left to put in what you think. Okay, let's take a look. Oh no, please stop beeping at me. Okay. The reveal, the counts. So, -1 everybody knows because I just told you. 22 people said the limit could be 1. That is correct, the limit could also be 1. And again, the reason you can get more than one limit is we're looking at more than one sequence of x values. So for the sequence of x values coming in from the left, the limit was -1. But there's another direction you can come at. You can come at from the left or from the right. And if you come from the right, it looks like this. So let me try to zoom in a bit so you can see exactly what's going on. The x values now are coming down to 1. So they go 1.3, 1.2, 1.1. And they're getting closer and closer to x equals 1 from the right side. And in this situation, the y values are coming down, but they get really close to y equals 1, not y equals -1 like they were before. And we can fill in this table of values just like we did before. So I can do, okay, maybe not. Here we go. We can fill in this kind of table of values when we are here at x equals 1.5, y is 2.25. Y is 2.25. And here, when we go down to 1.1, then y is 1.21. Y is 1.21. And when you get down to 0.01, then y is 1.02. 1.02. And if you continue this pattern, 1.002, 1.0002, the x values are getting really close to 1, just like before, but this time, because the x values came from the other direction, the y values get close to 0. So the x values are a bit more than 1. The x values are a bit more than 1, and y's get close to 1. So the y values are getting close to positive 1. And we can write this in a sentence as x approaches 1 from the right, f of x approaches y equals positive 1. Okay. So what is the moral of the story? Why am I making a big deal out of this? When we had sequences, there was only one kind of way you could approach the limit, right? You take n goes to infinity, the n values get bigger and bigger. That's the only thing you can do. When you have x's and y's, because we're talking about the x's getting close to a particular value, in this case, I'm doing x's getting close to 1. But even just something as simple as saying x's get close to 1 is not specific enough because there are multiple ways x could get close to 1. It could go to 1 from the left. It could go to 1 from the right. And it matters because in different situations, the y values do different things. So sometimes the y values will go to -1. Sometimes the y values will go to +1. It depends. OK, so we have to be careful. So what is the correct answer for this thing? If you guys in Math1030, let me reveal the right answer. Could the limit be -1? Yes. Could the limit be 1? Yes. What about the last thing? Could the limit does not exist? Also yes. If the limit could be -1 and the limit could be 1, there is a way to make the limit not exist. And all you got to do is alternate from the left and from the right. So if you're coming purely from the left, the limit will be -1. If you're coming purely from the right, the limit will be 1. Let me show you what it looks like when you're going both ways. And if you noticed in Desmos, I have this little folder called does not exist limit. Let's see what this looks like. So here is one that's bouncing around. It's going left, right, left, right, left, right. So sometimes it's on the left of x equals 1. Sometimes it's on the right of x equals 1. And by bouncing around, the y values never settle down. So the y values are going +1, -1, +1, -1, +1, -1. The y values never settle down. This one is also worth writing down, which you could write down maybe as a little sentence over here. You could say if x approaches 1 with no restrictions, then f of x approaches nothing. The limit does not exist. Nothing. I'm going to say approaches does not exist, which is not quite correct English, but is helping you at the idea. So this is a situation where you're coming in from one side, you get one thing, -1. If you come in from the other side, you get +1. And if somebody says, just go in towards x equals 1 and doesn't say left or right, then it could be that the limit does not exist because it's bouncing around like crazy. And here's the example, bouncing around like crazy. So we're going to have to deal with all these problems when we talk about limits as the x values go to 1. OK. Any questions or comments about this? OK. I'm going to say there's one other thing in the notes, which says the f of 1 equals blank. However, f of 1 equals blank. And this blank is very confusing, in my opinion. So I'm going to warn you guys. However, f of 1 equals blank. I'm going to highlight this and say all this stuff does not affect the limit, does not impact the limit. So I'm gonna highlight this and repeat it several times this lecture. Everything we've talked about so far is about the y values, what they get close to. This blank, f of 1 equals blank, is about what is happening exactly at x equals 1. What is the y value equal to? And this does not affect anything else. So I think this is more confusing than helpful. I'm going to cross it out. I'm going to cross this out, and I'm not going to answer what is f of 1 because it doesn't matter for our discussion. Our discussion is all about what happens when the x values get really close to but not equal to 1. What's going on at x equals 1 is irrelevant. So I'm not going to write it down because I think it will just confuse us. Like we'll have the wrong understanding. If we try to build a pattern based on what happens at f of 1, can we determine what the limit is? There is no pattern. So please don't think there is. So I'm going to cross it out. OK. And we're going to see more examples like that as we go forward. So this idea of approaching from one side or the other side, it has a name. We give it a name. We call them left and right limits. This is the picture we just did. The limit as x approaches 1 from the right, that was what I was doing in green. This was the value y equals +1. In Desmos, it was a nice animation. In your notes, we have a picture of a graph. How do we illustrate this nice animation on a picture of a graph? I am going to draw little arrows like this. So these little arrows are the picture representation of what is going on in Desmos. which is that the y values are getting closer and closer to something as the x values get closer and closer to x equals 1. So maybe x equals 1 was this line over here, x equals 1. And these little arrows represent a sequence. So I guess they're pairs, they're xn and yn, and xn's get close to 1, get close to x equals 1 from the right. Okay, so the xn's represent a sequence going down to 1 to x equals 1 from the right side. And I've drawn it as these little arrows. So hopefully you can see how those little arrows are like what we saw in Desmos. On the other hand, if you go in from the left, you get something else. So the limit of the f of x as you approach 1 from the left, that would be this sequence of arrows. So again, going in towards x equals 1, but from the other side. So this is xn's going to 1 from left. Okay, and in that case, we approached y equals negative 1. Y equals negative 1, which was this value over here. Y is negative 1 is what we were getting closer and closer to, whereas up here, it was y equals positive 1. And the important thing to realize is they are not equal in this situation. So they are not equal. Not equal. Okay, so that's something you got to watch out for. Nobody says they are equal. So the conclusion is we need a separate definition for the left and the right limit. That is what this notation means. And we're going to introduce these two symbols to mean these things. X going to a plus means you come in from the right, going in from the right, and it's this sequence of x values that come in on the number line from the right side. And we draw x going to a plus means x is a little bit bigger than a. On the other hand, x going to a minus is the exact opposite, coming in from the left. Okay. Does anyone know why I chose to use red for the left side and green for the right side? This is going to show if anybody goes on lakes in the summer. When you have a boat, you have to put a red light on the left side of your boat, and you put a green light on the right side of your boat, and then everybody knows which side is which. Except I just revealed I don't actually do this either because it's not left and right. It's supposed to be port and starboard. So the port side gets the red light, and the starboard side gets the right light, the green light. Okay. So we have left and right limits, and when the limits exist, like we just saw, we write this kind of thing. We say the limit as x goes to a plus, that is in green. The limit as x goes to a plus, this is the right-hand limit. And we write x goes to a minus for the left-hand limit. And when the y values get close to y equals some value L, then we say the limit equals L. So this represents y values get close to y equals L1, and this one represents the y values get close to y equals L2. Okay. So what we've seen so far, and we have this notation, it goes with the example we just did. Maybe I can freeze this for people who are still copying. Excuse me. So in the previous example we just did, the limits were from the right, the limit was positive 1, and from the left, it was negative 1. These mathematical statements are exactly the same as the thing we wrote as a sentence a few pages ago, but now it's written in symbols instead of words. But it means the exact same thing. Any questions or comments about that? So we had the idea of getting really close to from either side. We had these symbols that mean the same thing, and it's building on our definition of a limit from the limit of sequences, right? We're talking about the limit. What does the limit of the sequence of y values do? Okay. Questions, comments, anyone? So next up, you guys are going to do one, and I'm going to warn you that it might involve other things with limits we've seen. So with limits of sequences, we've seen what it means for the limit to does not exist. We've seen plus and minus infinity. We're building on that here. So here is a function, f of x equals 1 over x, and its graph is displayed. Please find these two limits. And that one I'm doing in Math1030. So you guys will have a chance to do this one. Okay, try it out. The limit of f of x equals 1 over x. I'll give you 2 minutes to work on that. Okay, 1 minute left. You should be half done. All right, 30 seconds. Okay. I'm going to give you 5 more seconds. Put in the answer. Okay. So let's take a look. Oh no. Please stop beeping. Thank you. Thank you. Okay. So let's see what you said. The limit as x goes to 0 minus, out of 32 people, some people said 0. Lots of people said 0. Let's look at the graph. Let's look at the graph. So the limit as x goes to 0 minus, I'm doing this one first. X goes to 0 minus means, look, as you get really close to x equals 0. X equals 0 is this, right? The y-axis, x equals 0. We're going to have x values getting really close to x equals 0, and we are going to ask the question, what do the y values do? So the way I would draw this is this kind of thing, right? We're on the graph of the function, and we are following along as the x values get really close to 0. And you can see what they're doing. They're kind of going off this cliff, and they're going down, 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 down. You can, let me do it one time in Desmos too. Let's make the function, okay, you stop. This stop, okay. Let's make the function 1 over x. There's the function. I want to look around x equals 0. There's the dotted line x equals 0. Turn these off. And we'll zoom out a bit. And then we're going to look at the left limit. What do the y values do on this side? The y values, what do? They go down. So they're going like this. The y values are going down, 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 down. Like we can sort of watch them fall off a cliff. They go zoop. I can try to catch them, but it's hard to catch them because they go pretty fast. Here they go. Oh, they zip by us. So the y values are shooting off down this cliff, and they're getting more and more negative forever. The y values are going to minus infinity. So this is, I would draw this as a picture. They're going down to minus infinity. So the limit, we say, is equal to minus infinity. This was exactly what we did when we did the limit of sequences. If the y value, if the sequence goes down forever and ever with no end and goes on forever and ever, the limit is minus infinity. So minus infinity is the right answer here. Lots of people said 0 over here. 6 people said 0. Maybe not that many people. Okay, so about half the people got that one right. What about the limit as x goes to 0 from the other side? Okay, this time, did lots of people say 0? Not so many this time. This one is infinity. This one is infinity. This one is infinity. Okay, and the reason is I would draw it on a 2-dimensional piece of paper like this. We're watching the x values go really close to x equals 0 from the other side. What do the y values do? Well, this time they go up, 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 up. And so from the right-hand side, when you're a little bit bigger than 0, it's plus infinity. So those are the limits. This question, I will warn you, what is f of 0 has nothing to do with limits, right? Everything we've done so far is about what is getting close to what, how things are moving around. F of 0, you could say, this is irrelevant for the limits. Irrelevant for the limits. Okay. In this particular case, it's the function 1 over x. What happens to 1 over x when x equals 0? It is not defined. So not defined, not defined, not defined, or does not exist would be another way to say it. The value does not exist. The function is not defined. How many people said does not exist? 21 people. That's fantastic. So very well done on that one. Minus infinity, infinity, and does not exist were the correct answers. Okay. Questions or comments about that one? That was a tricky one. Limits that don't exist, things like that. Okay. Here is another example. It's the function 1/2 x plus 1. I'm again going to do it by my little arrow method. I'm going to start with the limit from the left. X goes to 2 minus. These are values going like this. So the x values get really close to 2 from the left side. What do the y values do? They get really close to y equals 2, so the limit equals 2. The x values are getting really close in from this side, and the y values go up to y equals 2, so the limit is 2. What about the other side? What about the other side? On the other side, you're going like this. This is the limit as x goes to 2 plus x values that are a little bit bigger than 2. So what happens in this case? The y values, again, you get really close to the same y equals 2 over here. So the limit is 2. The limit from the left is 2, the limit from the right is 2. And this is exactly the situation where, again, what is the value f of 2? This is irrelevant. This has nothing to do with limits. This is irrelevant for limits. Irrelevant. I'm going to probably spell it a different way. Irrelevant for limits, right? The reason this was 2 and this was 2 is because we were getting close to y equals 2. What happens at x equals 2 doesn't matter. So in this situation, it's true the answer is 2, but it's a coincidence. But it's a coincidence. Coincidence. So don't think that because the value of 2 is 2, that's why the limits were 2. The limits were 2 because we were getting close to y equals 2. It just so happens in this particular case, that's also the value of the function, but that's not always the case. So don't get mixed up by that. That's why I'm drawing a line and telling you that's irrelevant, to watch out for that. Okay. So in this kind of situation, actually, I'll pause here for questions. Any questions about this thing? I think this idea of the limit is different than the value is sometimes confusing for people. Because in this case, they're equal. So you're like, oh, it's very tempting. It's so easy to do this. You just plug in the value. But it doesn't always work. It's a coincidence in this case. All right. So in this situation where the left limit and the right limit are the same thing, that is when we call it the two-sided limit. So the two-sided limit means it doesn't matter which side you come in from. So if you had done some kind of crazy alternating sequence in this example, because the left side is going up to 2 and the right side is going down to 2, it doesn't matter how you approach x equals 2. Any sequence going towards x equals 2 will also approach y equals 2. And in that situation, we say the two-sided limit is equal to 2. So here's the little definition. The limit, which is short for the two-sided limit, when it's equal to L, that means both the left limit, and the right limit exist and equal L. So another way to say it is, if it's true that the left limit and the right limit are equal, then we say that the two-sided limit is also equal to L. To the two-sided limit is L. And when we write the two-sided limit, we write the limit as x goes to a with nothing, no minus, no plus in the a. We just write x, arrow, a. So kind of implicit in this definition, and I'm going to write it out explicitly, which is the converse, which says that if the left and right limit are not equal, left and right limit are not equal, if the left and the right limit are not equal, what happens? So in the situation we just saw, the left limit was equal to the right limit, and then we say, aha, we're so happy we have the two-sided limit. If the left limit and the right limit are not equal, then the two-sided limit doesn't exist. Then the two-sided limit does not exist. Two-sided limit does not exist. I say like note. So they tried to say the limit exists means that the left and the right exist and are equal. So that means if the left and right are not equal, the limit does not exist. Okay. And I'll say one more thing. This is the two-sided limit. But if people just say the limit, they mean the two-sided limit. So if somebody says the limit does not exist, they mean the two-sided limit does not exist. Okay. So in particular, if we go back one page, let me freeze this for people who are still copying. But if you go back one page, this is our first example. In this example, the left limit and the right limit were equal. So you could additionally say that these two things together, they mean that, therefore, if the left limit is 2 and the right limit is 2, therefore, the limit with no lefts or rights, the limit as x goes to 2, the two-sided limit is also 2. So if they both exist and they're both the same, then that is the two-sided limit. Okay. Question here, maybe? No? Okay. All right. So we're going to do a few more examples. Exercise 177 is another example. We're going to compute the left limit, the right limit, and we're going to compute the two-sided limit. And we're going to compare that to the value f of 1. Okay, how would you do this? In this situation, because you have a picture, I would follow along the lines coming in from either side. So to do the left limit, we're doing the limit as x goes to 1 minus, that means left of x equals 1, on the left side over here. Left. So I'm going to follow in with my little arrows. The arrows go along like this. What do the y values do on that little piece of the function? The y values, in this case, are always 1. So the y value is 1 over here, then the y value is still 1 over here, the y value is still 1 over here, still 1, still 1, still 1. So the sequence of y values for any sequence here on the left is just 1, 1, 1, 1, 1. What is the sequence 1, 1, 1, 1, 1 doing? It's getting closer and closer to y equals 1. So this is y equals 1. And so the limit from the left is 1. Okay. So we're just imagining, again, you could do it in Desmos too as an animation. Imagine the thing sweeping over, the x values go from here to there, they get really close to x equals 1, and the y values are just always 1. On the other hand, we have the right limit on this side. And on this right limit, we're looking at x values that are a little bit bigger than 1. So all the x values over here, and we're thinking of the x values approaching x equals 1, but from the right side. So it's doing that little sequence of arrows like that. And in this situation, the values are always a half. 0.5, 0.5, 0.5, 0.5. What are they approaching? They're approaching y equals 0.5. So what is the limit? It's 0.5. Okay, very good. So we did the left limit by looking at the picture. We did the right limit by looking at the picture. Now we're going to do the limit, the two-sided limit. The limit with no adjective, just the limit. And that's x going to 1. What is the limit? The limit does not exist. This one does not exist. Does not exist. And you could say it does not exist because the left and the right limit are not equal. So as soon as the left limit is a half and the right limit is 1, they are not equal. Therefore, the two-sided limit does not exist. You could also say the reason the limit does not exist is because if you did one of these alternating bad boys that goes on the left, on the right, on the left, on the right, on the left, on the right, the limit of that sequence would not exist. So that is why, as soon as the left and the right are not equal, the whole limit does not exist. So you could say because left and right are not equal. Okay. So I'm about to fill in the value of f of 1, which, like I've said before, is irrelevant. But this is a good place to stop for any questions or comments. Yeah? That is a fantastic question. And the answer is it makes absolutely no difference. And the reason is the circle tells you what happens at f of x when x equals 1. And everything I've said so far about this thing is only about x values getting close to 1. So whether or not the circle is filled in has no impact whatsoever on any of those 3 statements. Whether or not the circle is filled in will affect this last statement, this last one in pink, what the value of f of 1 is, but does not have any bearing on those ones. Great, fantastic question. There's a question up here too, maybe? Maybe I saw a hand, maybe not. Yeah. Yeah. Yeah, why is f of 1 even on the page if it's irrelevant? Yes, so this is a great question. So later on, I've made this big deal of saying, don't look at f of 1. F of 1 doesn't tell you about the limit. This is the same way I could say for a rectangle. If we were learning about rectangles in grade 3, I would say to learn about rectangles, and if you want to know the height of the rectangle, the width of the rectangle is irrelevant. Don't think that the width of the rectangle tells you the height of the rectangle, right? And I would tell all my grade 3 kids, just watch out, the height and the width are different, don't mix them up, right? But then the next class, which is going to be on Monday for you guys, we're going to learn about squares. And in squares, the height and the width are the same. So for squares, knowing f of 1 will tell you the value of the limit. Yes, exactly. So today, I'm trying to tell you guys, make sure you know they're different. And in a couple classes, I'm going to say there's this special types of functions where they're equal, and then it's very nice. Yes, exactly, exactly, yeah. Yes, okay, that's another good question. So this function, it's kind of like, you're like, hey, this is kind of failing the vertical line test, right? Because I'm drawing this vertical line, x equals 1, and there's kind of like 2 y values on it. Totally true, everything's totally true. However, it's still a function. Why is it still a function? Because the vertical line test and this idea of a function with 1 input, 1 output is, again, about equals. So at x equals 1, at x is exactly equal to 1, at x equals 1 exactly, at x equals 1 exactly, there is only 1 y value. So that vertical line, even though it kind of has these 2 approaching businesses going on, it literally only has 1 value. And that value in this case is f of 1 equals 1 because the dot is filled in. So because that's filled in, it's f of 1 equals 1. It's a perfectly valid function, even though you're right, it's kind of like a bad function. But yeah, this is absolutely a good point. I'll give you guys a spoiler for next week. These bad functions, we have a name for them. They're called discontinuous. So this is an example of a discontinuous function. Discontinuous, continuous function. So it technically is a function still, but it has this bad label. Maybe I shouldn't be mean to the discontinuous functions. They're still functions, they just have this extra adjective. Yeah, great question. All right. Okay, so we've seen f of 1 equals 1, and I'm trying to warn you guys that f of 1 equals 1 has nothing to do with those limits. It has something to do with whether or not the function is continuous. We're going to see that next week. Okay. Other questions or comments? I'm going to let you loose to do this one, exercise 178, in just 1 second. Okay, go wild, go free on exercise 178. Okay, 30 seconds. Put in your guesses if you're not sure. Okay, let's take a look at what you guys said. The limit as x goes to 2 minus, most people think it's 2. It is 2, so very well done. And again, you can follow along by doing this kind of attack on the graph and seeing where do those y values go to. The y values are getting close to y equals 2, this line over here. The limit as x goes to 2 minus is 2. All right, good, we did that one. What about the other limits? The limit as x goes to 2 plus, still 2, still 2. That is correct. It's still 2. Why is it still 2? Because if you follow along on this side of the thing, on the right side, as the x values get close to 2 from the right side, they still get close to y equals 2 for the y values. So the limit as x goes to 2 from the right is still 2. Those two are pretty easy. The third one, this is one people often get this one wrong on exams and things. This is the one that most people would get wrong on an exam. Let's see if you guys got it right or wrong. The limit as x goes to 2, the two-sided limit. What is the two-sided limit? 20 people think it's 2. 5 people think it does not exist. Does not exist is the answer. That is the common incorrect answer. The correct answer is 2. It's 2. The two-sided limit is 2. And again, the reason it's 2 is because the left and right limit are both 2. Because the left equals the right equals 2. So the left limit is 2, the right limit is 2, therefore the limit is just 2. That's it. So a lot of people get confused. They think there's like a hole here, which there is a hole in the graph, but the hole does not affect what you're getting close to, right? The hole is about what is happening exactly at x equals 2. We don't care about what happens at exactly x equals 2. We care about what happens when you get close. That information is encapsulated in the value f of 2. Let's see if you guys correctly identified the value of f of 2. Aha. So some people, 9 people said f of 2 does not exist. That is incorrect. The value of f of 2 does exist. The value of f of 2 is 0. How do I know the value of f of 2 is 0? Because it is on the ground right here. Look, there's f of 2, right? That filled in dot on the ground, because it's filled in, that means that is the value of f of 2. So f of 2 equals 0. Let's do this one in pink. And a lot of people get confused by this situation. This is a situation where the value of the function is different than the value of the limit, which is totally fine. Limits are just about what you're getting close to. Nobody says that the value of the function has to be equal to the value of the limit. Everything is fine here. Everything exists. There are no does not exist. F of 2 equals 0, and the value of the limits are all 2. So if you are confused by this, if you think one of them should not exist, it is a sign that you're misunderstanding something about the idea of a limit. So this is a really good one. If this is confusing at all, or you got the wrong answer, really just like double check, go back and try to rethink of your mental model of what is a limit. This will reveal if that's incorrect. And again, I'm going to say f of 2 equals 0. And that is irrelevant for determining the limit. Irrelevant for determining the limit. The limit. Okay. Questions or comments about that one? So what else is in, what have we done so far? We have learned what a limit is using pictures, right? We've learned these graphical ideas of getting close. You can also do it algebraically. So here is an example with algebra. There is no picture to go with this one. You can also do this left and right hand limit business with the algebra. So let's do this one. We're going to do these two limits. The limit as x goes to 1 plus and x goes to 1 minus. Let me fill them in with my colors because I like my colors today. X goes to 1 minus and x goes to 1 plus. And we're doing the function f of x. And I want to figure out what these are using algebra instead of using the picture. And this is a piecewise function, so you have to remember piecewise functions from earlier in the course. This is a piecewise function with two parts. It has one part when x is less than 1, and it has another part when x is bigger than 1. And when you're doing a one-sided limit, like this limit as x goes to 1 minus, then you're only going to be using 1/2 of that function. So x goes to 1 minus, this means x is less than 1, right? Coming on the left side of 1 on the number line is x is less than 1. And when x is less than 1, the function is equal to 1, right? The function is equal to 1. That's what it tells me. F of x equals 1 for x less than 1. So what is the limit? It's the same as the limit as x goes to 1 minus of the function, the value that is always 1. Let's do it in purple. 1. So this 1 over here is what I'm talking about. The function is always 1 if x is less than 1. So what is the limit? Well, it's the limit of 1. 1, 1, 1, 1, 1. OK, so that's 1. 1. Let's do the other side. On the other side, x is bigger than 1. That's over here. Here, x is bigger than 1. And if x is bigger than 1, we're going to use this part of the function, right? When x is bigger than 1, the value of the function is 1/2. So it's the limit as x goes to 1 from the positive side of 1/2. So the function is always 1/2. And so what is the limit of the thing that's always 1/2? It's just 1/2. OK. So the limit from one side is 1. The limit from the other side is 1/2. This might seem familiar. We did an example earlier today. This one was all algebra. But we did one that was a picture that was just like this. It was this one. So we did this one earlier as a picture, and we said, you're getting close to 1, look at the pictures. You're getting close to 1/2, look at the pictures. Now we've done it two ways. That function is exactly the same as the function that was written with algebra. What is the point of this? It's to show you that you can do limits either with algebra or with pictures and understand what the limit is. There are a few other examples in the notes. I will post extra videos with those. Next class, we're going to start learning how to calculate limits with algebra. So we're going to learn some algebra tools to calculate limits. OK, I'll be around for a few more minutes if you have questions. But otherwise, see you guys on Monday.